Hello everyone and welcome back to the channel. Today we are looking at a notorious volumetric analysis question that completely devastated student scores across the state, with over 60% of students scoring a 0 on the error analysis portion. Most students saw the word rinsing and assumed the issue was just about adding extra pure water to the flask. But they completely forgot one critical detail: we are titrating cooked spinach. In this video, I will show you why that minor oversight turned a straightforward titration problem into a massive statewide trap, and how you can avoid making the exact same mistake on your final exam. Let us dive straight into the chemistry. Irfan is conducting an experiment in which two aqueous solutions, hydrogen peroxide, H2O2, and a vitamin C solution are reacted together in a beaker. This reaction is known to have a delayed, but obvious color change. The vitamin C solution is prepared by crushing a vitamin C tablet and dissolving it in deionized water, then adding iodine, I2. Irfan is investigating how changing the concentration of vitamin C in the solution affects the time taken for the color change to occur. The concentration is changed by adding different volumes of deionized water to 5.0 milliliters of the vitamin C solution before reacting it with H2O2. Irfan repeats the experiment twice for each concentration. The diagram shows 4 pieces of volumetric apparatus. Each one has graduations, but they don't share the same level of precision. The core task here is to carefully read the question and compare the resolution of each instrument. 1. Eliminating the obvious wrongs, options A and B. First, let's look at the beaker. As we know, a beaker is never qualified as a precision instrument for measuring volume. It is simply a container used for holding or mixing liquids. Looking at the markings, its scale goes up in coarse 10 milliliters blocks, giving it the lowest resolution of the group. Because options A and B claim the beaker has the highest resolution, we can cross them off straight away. 2. The pipette trap. Why many students chose option D. Next, let's address why a lot of students fell into a trap and chose option D. Generally, students are taught that a pipette is the most precise tool in a chemistry lab. While that is true for standard analytical glassware, which often measures down to 0.01 milliliters, we have to look at the specific tool provided in this experiment. If you look closely at the zoomed-in view of this 3 milliliters plastic graduated pipette, the scale only goes up by 0.5 milliliters increments. Because its resolution is actually coarser than one of the measuring cylinders, the pipette is not the highest resolution tool de facto. This subtle detail is exactly why option D misled so many students. Three. Finding the correct sequence. To find the true ranking from lowest to highest resolution, we just need to list out the smallest increments each tool can read. 50 milliliters beaker, 10 milliliters increments lowest resolution. 50 milliliters measuring cylinder, 1 milliliter increments. 3 milliliters graduated plastic pipette, 0.5 milliliters increments. 10 milliliters measuring cylinder, 0.2 milliliters increments, highest resolution. Since a smaller numerical increment means a finer, higher resolution, the correct order from lowest to highest is beaker, 10 milliliters. A graph showing the time for a color change to occur versus the amount of deionized water added is shown below. Which one of the following factors is most likely responsible for the variability shown in the graph above? 1. Identifying the nature of the error. First, we must look at how the data deviates. Because the data points lie both above and below the line of best fit, the variability in the graph must be due to random error. Furthermore, because there is no theoretical reference line plotted for comparison, we cannot establish whether any systematic errors are present. We are strictly looking for a source of random fluctuation. 2. Evaluating the options. Option A, judging when the color change occurs correct. The iodine clock reaction features a delayed, but sudden color change. Detecting this exact transition relies on the subjective observation of the experimenter. Because human reaction time and visual perception vary slightly from trial to trial, this introduces a natural, two-sided fluctuation. This subjective observation is the greatest source of random error in the experiment, perfectly explaining why the data points scatter on both sides of the line. Options B and C, incorrect. Option B, volume of iodine remaining in the pipette tip, and option C, some vitamin C tablet not completely dissolving, would introduce a systematic error rather than a random one. If vitamin C fails to dissolve fully, the concentration is consistently lower than intended. If liquid is always left in the pipette tip, the delivered volume is consistently less. This would shift the entire trend line in one direction, altering the slope or intercept, but would not cause the data points to dance randomly above and below the line. Option D, changes in laboratory room temperature incorrect. Ambient room temperature does not fluctuate wildly back and forth between consecutive trials. For temperature to produce the random errors shown in the graph, it would have to significantly increase for some trials and significantly decrease for others in a matter of minutes. Since room temperature remains relatively stable, or shifts linearly over time, it cannot be responsible for this distinct random variability. Therefore, option A is the One mole of a triglyceride containing only one type of fatty acid reacts completely with 6 moles of iodine, I2. Which one of the following could be the fatty acid? This question requires us to determine the identity of a fatty acid based on how its triglyceride reacts with iodine, I2. Let's break down the chemistry behind the examiner's brief comment. Step 1. Determine the number of C=C double bonds per fatty acid. The reaction described is an addition reaction. Iodine, I2, reacts across carbon-to-carbon double bonds, C=C, in unsaturated fat chains. The fundamental ratio, exactly 1 mole of I2 reacts with 1 mole of C=C double bonds. The prompt states that 1 mole of triglyceride, 6 moles of I2. This means there are a total of 6 moles of C=C double bonds in 1 mole of this specific triglyceride. However, remember the structure of a triglyceride. It is a triester formed from 1 glycerol molecule and 3 fatty acid tails. The question specifies that this triglyceride contains only one type of fatty acid. Therefore, we divide the total number of double bonds by the 3 fatty acid chains, and find that 1 mole of I2 reacts with 2 mole C=C double bond per fatty acid chain. Once we calculate that each individual fatty acid chain must contain exactly 2 C=C double bonds, we can open our VCE data book to the fatty acids table and read the semi-structural formulas directly. Option A, linolenic. Notice the subscript outside the bracket, CH2CH = CH3. This means this unit repeats 3 times. 3 double bonds. Option B, linoleic. Scan across the chain and we see 2 distinct CH = CH groups. 2 double bonds. Option C, oleic. Contains exactly 1 CH = CH group. 1 double bond. Option D, stearic. No CH equals CH groups present. 0 double bonds. When students look at question 29, their eyes immediately lock onto the number 6. The most common incorrect thought process goes like this. 6 moles of iodine means 6 double bonds. Let me look at the data book for a fatty acid with 6 double bonds. This calculation completely implodes because the student treated the triglyceride and the fatty acid as the exact same thing. Let's break down the structural reality to show why they are completely different tiers of organization. A fatty acid is a single hydrocarbon chain terminating in a carboxyl group, COOH. A triglyceride, however, is a much larger composite molecule. It is formed via a condensation reaction, where 3 individual fatty acids are chemically linked to a single glycerol backbone via ester bonds. The molecule in the reaction, the question states that 1 mole of a triglyceride reacts with 6 moles of I2. The target of the question asks, which one of the following could be the fatty acid? Many vegetables contain compounds that taste bitter because of the oxalate ion. Removing the bitterness can be achieved through different cooking methods, including boiling and steaming. VCE chemistry student Karolina undertook research to collect background information for her scientific investigation and learned that oxalate compounds can be water-soluble and water-insoluble. From her research, Karolina developed the following hypothesis. The boiling process will remove 75% of the oxalate compounds in spinach leaves. Karolina tested her hypothesis by investigating the effectiveness of boiling to remove oxalate ion from spinach leaves. This question asks students to identify the specific methodology Karolina used to develop her hypothesis. To find the answer, we need to look straight at the clues hidden in the introductory text. The stem tells us. VCE chemistry student Karolina undertook research to collect background information for her scientific investigation and learned that oxalate compounds can be water-soluble and water-insoluble. From her research, Karolina developed the following hypothesis. Notice what she is doing here. Before she ever steps foot into the laboratory, she is reading papers, looking at textbooks, or studying data tables to find out what is already known about oxalate compounds. She is gathering secondary data to build her rationale. By definition, this process of evaluating existing secondary data to establish context or formulate a theory is exactly what a literature review is. It is absolutely staggering that 57% of the state cohort received 0 marks on this single-mark question. When more than half of the students get a multiple-choice question wrong, it usually means they fell into a classic concept trap. In this case, students confuse different types of scientific investigations. Let's review the core VCE definitions to make sure you never make this mistake again. Controlled experiment. Changing one variable in a lab to measure another while keeping everything else constant. What Karolina did later via titration to test her hypothesis. Literature review, reading textbooks, papers, or data tables to find out what is already known. What Karolina did to form her hypothesis. Fieldwork, going out into an ecosystem or real-world environment to observe and gather data as it naturally occurs. Modeling, using mathematical equations, physical replicas, or software to mimic a real-world system. Would you believe me if I told you that 78% of VCE chemistry students across Victoria got a flat 0 on a single-mark titration question? 78%. We aren't talking about a complex, multi-step calculation here, we are talking about a simple, one-word observation question. The examiners didn't set an unfair trap, the students simply walked right into it because they relied on a memorized textbook phrase instead of slowing down and reading the question stem. Let's break down the notorious question 6b, pull apart why the word pink utterly destroyed thousands of student scores, and make sure you never fall for this data book trap again. Let's do what 78% of the state failed to do, read the stem line by line. The prompt gives us a redox equation. Then, Part B says, refer to item 7 of the data book. What specific observation did Karolina use to determine the end point of the titration? When the exam explicitly tells you to look at a specific item in the data book, that is your first major warning sign. It means your memory alone is not enough, there is a specific constraint on this page you must obey. MN041 is listed as purple. MN2+ is listed as pink. How to find the true endpoint? We should refer the process titration. Stage 1, before titration. The flask contains colorless analyte. The burette is filled with deep purple titrant. Stage 2 and 3, during titration, the trap. As purple permanganate ions enter the flask, it reacts to produce manganese ions. Item 7 of the VCE data book explicitly states that manganese ions are pink. Because this product builds up continuously, with every drop, the background solution naturally turns pink while the reaction is still actively occurring. Stage 4, the true endpoint. Once the analyte is completely exhausted, the very next drop of deep purple permanganate ions has nothing left to react with. It remains unreacted in its original form, tinting the solution with the first permanent purple color, or purple tint. Why pink is completely disqualified? Because the solution is already becoming a steadily forming pink due to the accumulation of manganese ions. A shift to pink does not signal that the reaction is over. High-scoring written summary for students. The real end point only happens on the very first drop of excess permanganate ions. When all the oxalate is completely consumed, that next drop of permanganate ions has nothing left to react with oxalate. It stays exactly as it is, purple. The perfect answer. The solution changes to the first permanent sign of a purple color. The reaction was conducted at 50 degrees Celsius rather than at room temperature. Use collision theory to state why this is a preferred temperature at which to conduct the reaction. 1 mark. This is standard Unit 3 rate chemistry. When you heat up a reaction system, you are directly increasing the kinetic energy of the particles. According to collision theory, this means two things happen. The particles move faster, leading to a higher frequency of collisions. A greater proportion of moving particles will possess energy equal to or greater than the activation energy, resulting in a higher percentage of successful collisions. Ultimately, both factors lead to a faster rate of reaction. The examiners kept it simple. As long as you recognized that the increased temperature caused a faster reaction rate, you secured the mark. Because it is a redox titration, a fast reaction ensures that the purple color of each incoming drop decolors instantly until the exact moment the analyte runs out. At 50 C, reacting particles possess higher average kinetic energy, increasing the frequency of collisions and the proportion of collisions with energy equal to or greater than its activation energy. This results in a faster, more optimal rate of reaction for the titration. Now let's look at Part 2, which reads, "State why the experiment might no longer be valid if the reaction is conducted at room temperature." This dropped the state average down to 66%, because the moment VCE examiners use the word valid, or validity, students tend to freeze. They forget what validity actually means in a scientific investigation. VCE core definition: an experiment is valid if it actually measures what it claims to be measuring, and if the methodology perfectly aligns with answering the original aim and hypothesis. The examiners accepted two brilliant pathways to link room temperature to a loss of validity. Pathway 1, the chemical consequence, reaction is too slow. If you conduct this specific oxalate permanganate titration at a low room temperature, the reaction rate becomes incredibly sluggish. When you drop the purple permanganate ions into the flask, it won't react instantly. Because it takes a long time to decolor, you might assume you've reached the permanent endpoint when you haven't. This slow rate makes it impossible to accurately measure the true equivalence point, meaning your final calculations will be completely wrong. You are no longer measuring the true concentration of oxalate. Pathway 2, the methodological flaw, violating the hypothesis. Let's look back STEM. What was Karolina's original hypothesis? The boiling process will remove 75% of the oxalate compounds in spinach leaves. Her entire investigation is explicitly designed to isolate and test the effect of boiling. If she runs her extraction or subsequent titration steps at a variable room temperature, instead of following the strict thermal control required by the methodology, she is no longer testing the impact of the boiling process. The step becomes invalid because it deviates completely from the design required to test her specific hypothesis. Option 1, the chemical pathway, focus on reaction rate. At room temperature, the reaction rate is too slow. The purple titrant will not decolor instantly upon entering the flask, making it impossible to observe a sharp, accurate endpoint and resulting in invalid data. Or Option 2, the methodological pathway, focus on the hypothesis. The experiment becomes invalid because the original hypothesis explicitly aims to test the impact of the boiling process. Conducting the steps at room temperature deviates from the required controlled conditions. The VCE Validity Checklist. Remind your students that to score a mark for validity, their answer must always connect the change in conditions directly to a failure in the experimental process. Slow rate, can't measure the true endpoint, invalid data. Wrong temperature, fails to test the actual hypothesis, invalid process. Let's look at question 6D. On the surface, this looks like a free mark. The question simply asks you to calculate an average titer from a data table. Yet, 35% of students across Victoria scored 0. Why? Because they saw 4 numbers and immediately did what they learned in middle school math. They added all 4 together and divided by 4. In VCE chemistry, blindly averaging your raw data is a guaranteed way to throw away marks. Let's look at the data table and learn how to identify what actually belongs in your calculation. Whenever you are asked to calculate an average titer in a VCE exam, your mind must immediately trigger the phrase, concordant titers. You only calculate the average using concordant titers. By definition, concordant titers are a set of 3 or more titers that fall within 0.10 milliliters of each other from highest to lowest. Note, some specific practical guidelines accept 2, but for VCE exam data tables, always look for the tightest cluster within 0.10 milliliters. Let's evaluate the 4 titers Karolina recorded. Trial 1, 16.10 milliliters. Trial 2, 15.45 milliliters. Trial 3, 15.40 milliliters. Trial 4, 15.40 milliliters. If you look closely at Trial 1, 16.10 milliliters, it is wildly different from the others. This is an outlier, likely a rough first trial where she overshot the endpoint. Including this outlier is exactly how 35% of the state lost their mark. Now look at Trials 2, 3, and 4. The highest value is 15.45 milliliters. The lowest value is 15.40 milliliters. The maximum range between them is 15.45. 15.40 is equal to 0.05 ml. Because 0.05 milliliters is less than or equal to the strict 0.10 milliliters VCE limit, Trials 2, 3, and 4 are our concordant titers. Trial 1 must be completely excluded from your math. Here is how students should lay out their working to secure the mark instantly. 16.10 milliliters is an outlier. Only use concordant titers, Trials 2, 3, and 4. This 4-mark volumetric calculation completely destroyed student scores on the VCE exam, leaving over a third of the cohort with a flat 0 and only 13% with full marks. How do you master it? We are going to use a clean, 4-step logic ladder to break down this question, navigating from the burette, crossing the mole ratio bridge, factoring in the dilution, and calculating the final mass. Let's find out how to secure all 4 marks. Step 1. Calculate amount of titrant used. We always start where we have the most complete pieces of information, the burette. We know both the concentration and the exact average volume of our potassium permanganate. Step 2. Cross the stoichiometric bridge, the aliquot. Now we need to figure out how much oxalate reacted with that specific amount of permanganate inside the conical flask. To do this, we look at the coefficients of our balanced chemical equation from Part B. Step 3. Account for the dilution factor, the large flask. Remember that concentration of oxalate was only inside the small 25.0 milliliters sample, aliquot, drawn from the big flask. We need to scale this up to find out how much total oxalate was extracted into the full 500 milliliters volumetric flask. Step 4. Convert moles to mass. Finally, we have the total moles of oxalate extracted from our 15.1 g sample of spinach. The question asks for the final answer in grams, so we multiply our total moles by the given molar mass. Think you've survived the hardest parts of the exam? Think again. A mind-blowing 83% of VCE chemistry students got a flat 0 on this final, single-mark percentage change calculation. Today, we are going to look at question 6F and pull apart the exact mathematical traps, including an unexpected rounding hazard that completely wiped out over 4/5 of the state. The question asks us to determine the percentage change of oxalate ion that resulted by boiling the spinach in this experiment. Let's look at why it completely destroyed the cohort. When calculating a percentage change, reduction or increase, the initial state is always the baseline boundary condition. Initial mass, uncooked or raw spinach from 6e 0.136 g. Final mass, cooked spinach from 6f 0.0545 g. Thousands of students made the classic percentage error of placing the smaller, cooked value, 0.0545 g, in the denominator, or simply dividing the cooked mass by the raw mass without calculating the change first. High-scoring takeaway rule for your students. The golden rule of multi-part VCE questions. Never carry a finished, 2 SIG fig rounded answer into the next sub-question part. Always keep a clean copy of your data saved in your calculator's memory or written down to at least 3 or 4 significant figures, 0.136 g, to use for subsequent steps. Otherwise, rounding compounding errors will cost you the mark. Look closely at the stats for question 6G. 61% of the state scored a flat 0, and only 5% achieved full marks. Why did this happen? Because thousands of students failed to identify the actual subject of the titration, the cooked spinach sample. Students blindly assumed that insufficient rinsing simply meant leaving extra pure water on the leaves, which they thought would dilute the solution. But remember what Karolina just did: she boiled the spinach. During boiling, a massive amount of highly soluble oxalate ions leached out of the plant cells and into the boiling water. Therefore, the water clinging to the unrinsed, cooked leaves isn't pure water, it is a concentrated oxalate soup. When we proceed to extract the remaining oxalate from these cooked leaves, that external residue gets mixed right into our flask, completely corrupting the data. The two-step logic ladder: to secure both marks seamlessly, students must establish this exact cause and effect chain. Step 1. Cause. Insufficient rinsing leaves oxalate-rich cooking water on the outside of the cooked leaves. Step 2. Effect. This extra surface oxalate is carried into the extraction phase. Increases the total moles of oxalate in the conical flask. Requires a larger titer of kmNO4 to reach the endpoint. Results in an artificially higher calculated concentration. Memo: high scoring exam response template. Insufficient rinsing leaves residual cooking water on the exterior of the cooked spinach leaves, which contains dissolved, leached oxalate ions. This accidentally adds extra oxalate into the sample being analyzed. 1 mark. Because there is extra oxalate in the flask, a larger titer of permanganate is required to reach the endpoint, resulting in an artificially higher calculated oxalate concentration. 1 mark. Left-pointing magnifying glass hypothesis versus results, the scientific analysis. The baseline hypothesis. Karolina's original prediction was a specific 75% reduction in oxalate content due to boiling. The empirical result. The actual titration calculations from Part F yielded a 60% reduction in oxalate mass. Because 60% is significantly lower than 75%, the real-world evidence simply does not match the prediction. Therefore, the findings do not support the hypothesis. This highlights an important VCE scientific skills lesson for students. A hypothesis doesn't need to be right to get full marks. The student's job is simply to evaluate it honestly using their data. Step-by-step breakdown: the evaluation trap. The command term here is discuss, which means students must do more than just say yes or no. Mark 1. Clearly identify what the initial hypothesis actually predicted, which was a 75% reduction. Mark 2. Explicitly compare your calculated experimental value from Part F to that 75% benchmark to conclude if it supports it or not. Answer model. Since the calculated result from Part F was only a 60% reduction, the experimental data does not support the original hypothesis, because the actual reduction was significantly lower than the predicted 75%. When VCAA uses the command term discuss in a hypothesis evaluation, they are looking for precise data linking. If a student writes, Crossmark, the hypothesis is not supported because the boiled spinach had less oxalate change than Karolina thought. Crossmark, the hypothesis is wrong because 60% is lower than the hypothesis. They will likely score 0 out of 2. Why? Because they fail to explicitly reference the specific benchmark set by the experiment. To guarantee full marks, the response must be explicit. It must name the 75% from the hypothesis. It must compare it directly to the calculated 60% from Part F. Key exam takeaways. Resolution is the smallest increment a tool can read. A smaller increment is finer, so the beaker ranks lowest and the 10 ml cylinder highest, Q19. Data points scattered on both sides of the line of best fit signal random error, not systematic error, Q20. Divide the total C equals C double bonds by the 3 fatty acid chains. 6 moles of I2 per triglyceride means 2 per chain, Q29. Read the question stem before reciting data book phrases. Wording like pink cost thousands of marks, Q6b. Carry unrounded values, 3 to 4 significant figures, between multi-part calculations to avoid compounding rounding errors, Q6ef. Discuss demands explicit data linking. Name the predicted 75% reduction, and compare it to the calculated 60%, Q6h. Question by question recap. Q19, and Q20, A ranking apparatus resolution, and identifying the source of random error. Q29, B linoleic acid, 2C equals C double bonds per chain. Q6a identifying the methodology, the titration endpoint color, and the average titer. Q6ef, calculating oxalate mass and the percentage change after boiling. Q6gh, why rinsing the cooked spinach matters and evaluating the hypothesis honestly. If you need my help, please add me on WeChat or WhatsApp and send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.